Title is less is more. Focus attention for efficient DETR. Object detection is crucial in CV and to meet performance constraints on edge devices and AI chips. Lightweight models are vital. Transformers have revolutionized object detection, leading to several DETR-like models. With 3 key innovations, these measures include deformable attention, DINWAS, and structure optimization. We've drawn from achievements in lightweighting visual transformers, focusing on token pruning, compression, and structural adjustments. These strategies speed up training or inference. Our focus was on optimizing the encoder due to higher flops compared to the decoder. Unlike past approaches, we incorporated contemporary query construction methods, efficiently training the token pruning module and compensating for information loss in deformable attention by integrating long-range interactions are also key hurdles. Addressing these challenges is vital for achieving our optimized model design. Our work addresses key drawbacks in prior approaches like sparse DETR and PNP DETR. Sparse DETR's performance boost in deformable DETR, but not in other models, is due to the discrepancy in pseudolabel. It struggles with multi-scale semantic correlations, leading to inconsistent foreground token distribution. PNP DETR compresses background tokens, reducing computation but disrupting spatial information. Focus DETR comprises backbone, dual attention encoder, and decoder. The backbone, either ResNet or swing transformer, generates multi-scale feature maps. We perform foreground token selection before the dual attention encoder using top-down score modulations. This selector identifies foreground tokens, then we use dual attention to enhance long-range interaction among fine-grained tokens. In contrast to DINO, focus DETR drastically reduces encoder demands, employing just 30% of foreground tokens. This results in a 65% flops reduction. The dual attention semantic enhancement adds a mere 1G FLOPS increase and is negligible. Our calculations show a 7-fold higher flops in the encoder. The dual attention mechanism introduces just a negligible 0.25% extra computation in the overall transformer structure. The right figure illustrates the areas retained by our foreground selection and self-attention enhancement modules, highlighting our more precise foreground selection than sparse DETR. Semantic correlations between multi-scale feature maps are vital for effective foreground-background selection. To avoid repeated selection of similar target positions, we introduce a top-down score modulation mechanism. It attenuates adjacent low-level semantic feature map scores using higher-level ones, preventing repetitive selection and enhancing accuracy. This concept is shown in the algorithmic flow. We've assessed limitations in pseudolabel supervised foreground selection, drawing from FS foreground-background label construction. We've optimized for focus DETR. In focus DETR, we use geometric mapping to convert original bounding box labels into foreground-background labels. This transformation involves setting scale overlap ranges, boosting prediction accuracy for feature maps. This strategy aims to improve foreground selection precision. Before discussing experimental results, we provide visual insights into our approach. In the left figure, we visualize how focus DETR retains accurate foreground features and uses semantic correlations across different scale feature maps, enabling precise predictions for varied scales. To enhance early prediction reliability, we cascade foreground selection in the encoder, progressively narrowing retained regions. The right figure shows this reduction across encoder layers in focus DETR. Extensive dataset testing of focus DETR against numerous models highlights its strengths. Compared to DINO, focus DETR achieves impressive results, a 45% flops reduction, about 40% higher FPS, with only a marginal 0.5% accuracy drop. This solidifies focus DETR as an efficient detector. Replacing RESN ET50 with RESN ET101 backbone yielded an impressive 51.4 AP accuracy at just 2 to 1 GFLOPS. The AP flops relationship is depicted in the right figure, illustrating focus DETR's optimal balance between performance and resource usage. Table 4 outlines focus DETR's component impact on detection performance. Table 5 analyzes the influence of top-down vs. bottom-up modulation in the score modulation module. Table 6 showcases DINO's performance variations with sparse DETR and focus DETR. Table 9 validates focus DETR's performance with swing transformer and assesses training convergence across different backbones, including comparison with DINO. To reinforce focus DETR's versatility across DETR-like models, the experiments on DNDETR and DEP DETR were conducted. Results highlight focus DETR's advantages. Thank you for your attention.